Okay, so what we're going to do, we are looking at lesson 13, and this lesson deals with isotopes. So some things we have to understand: all atoms of an element are not necessarily identical to one another. We know that elements are comprised of atoms of only that element, but there are some cases in which elements are not the same. So it's not like we're going into Willy Wonka where we have the Oompa Loompas that all look exactly the same for the most part. We have some elements that have atoms that have some differences in the nucleus. Okay. So while the number of protons in the nucleus of an element is the same for all atoms of an element, because remember, we learned if we change the number of protons, then we are changing the element that we have. But the difference in that nucleus comes from the number of neutrons. Okay, so remember, if we change the number of neutrons in the nucleus, we're also going to be changing the mass of that specific atom, not of the whole entire element, but of that specific atom. Okay, atoms of the element that have different numbers of neutrons, we call these isotopes. So that's our key focus here. The average atomic mass of an element that we get on the periodic table, remember that is the decimal number. This is the weighted average of the atomic masses of the isotopes of that element. Okay, so the learning goals that we have here, we're going to define isotope. We are also going to be able to write and interpret symbols for specific isotopes. Okay, we're also going to be able to determine the average atomic mass of an element based on the natural abundance of the isotope of that element. And then we are also going to be able to predict the number of protons, neutrons, and electrons that are most abundant in terms of the most abundant isotopes of that atom, given the average atomic mass. Okay, so some key terms that we have here. We have isotope, so atoms of the same element that have different numbers of neutrons. The number of protons is still going to stay the same, but we're going to have different numbers of neutrons. Okay. The average atomic mass, that's that weighted average of all of the decimal numbers. And I briefly talked about this when we started to learn in lesson 12, the difference between a mass number and an average atomic mass. We said, hey, we have an atomic number, and that is a whole number on the periodic table. And then we have that decimal number, which is the average atomic mass. The reason why it's not a whole number, why the mass is not a whole number, is because we have one or more variations of the atom of that element. Okay, the mass number, this is the sum of the protons and the neutrons in the nucleus. So after we've come through learning about the atomic theory, we have learned that protons and neutrons are found inside of the nucleus. The protons have a positive charge, neutrons have no charge, but they do have, a pretty much identical mass there. Okay. So let's do a little bit of learning here. Well, let's talk, let's look at some examples. So a chemist is investigating a sample of lithium that they found it has some lithium atoms that have a lower mass than other lithium atoms. Okay, so the chemist drew models of the two different types of lithium atoms that we see here. Okay, so I'm going to go ahead and I'm going to draw a number 1 and a number 2 here so you can help me differentiate here. We have these two different models. Easy. Okay, so let's take a look. Let's talk about, what do they have the same? Well, they have the same number of little places where we can find electrons. They both have 3 electrons that you can see here. Remember, those electrons orbit on the outside of the nucleus. Okay. Let's look in the nucleus. 1, 2, 3, 4, 5, 6. We have 6 particles in the nucleus here. Here we have 1, 2, 3, 4, 5, 6, 7. Here we have 7 particles inside of that nucleus, okay? So the difference between these two atoms of lithium would be what we find inside of their nucleus. So the number of particles that we have in there. Okay, well, let's think about this. Lithium. If we look at our periodic table, we have to be able to understand that each atom will have the same number of protons of lithium. So that means all of these have an atomic number of what? It should be 3, okay? And we know that since we're dealing with basically just neutral atoms, so the number of protons and the number of electrons should be the same. Our positives and our negatives balance out to give us 0. Since we have 3 electrons, we obviously must have 3 protons, okay? And that would be the same for atom 1 and atom 2, okay? Number 3, what is the atomic mass of each atom? Well, when we look at atomic mass, we have to add up the numbers of particles that we find inside of the nucleus, so it's protons plus neutrons. Doesn't matter which is which based on this picture we have here, but for atom 1, the mass is 6. For atom 2, the mass is 7. Okay? All right. So atoms of the same element that have different numbers of neutrons, we call these isotopes. For the most part, elements have more than one of these. Okay. Most elements consist of more than one type of isotope, differing by only the number of neutrons in their nucleus. Okay. Everything else about them is identical. So the number of protons, the number of electrons should be the same. Okay. If 2 atoms have different numbers of neutrons, it means that their atomic masses of those 2 atoms won't be the same, even though they are atoms of the same element, okay? That basically means their numbers of protons and neutrons will be, their number of protons and electrons will be the same, but their number of neutrons will be different. If you look at these 3 pictures that we have here, these are 3 different isotopes for carbon, okay? And you can see from their symbols that are listed down here, okay? For example, I just circled this. These are our symbols. So we have an isotope of carbon with a 12 up top, one with a 13 up top, and one with a 14 up top. Well, we have to figure out, what does that mean? We will learn in this lesson, but let's take this moment to go over it, okay? If we look inside of the nucleus of each atom, okay, you will see pink spheres, you will see yellow spheres with positive signs in them or plus signs in them. So let's assume that these plus signs are protons, okay? Take a look. We have 6 protons in this nucleus. We have 6 protons in this nucleus. We have 6 protons in this nucleus, okay? Well, let's count the number of pinks. So we have 6 neutrons, right? Because that's what else is in a nucleus. We have 7 neutrons, and we have 8 neutrons, okay? 6 neutrons, 7 neutrons, 8 neutrons. Notice they're all isotopes of carbon. They all have the same number of protons, but their nucleus is different because they have different numbers of neutrons, okay? Well, let's try to figure out what these symbols down here mean. Well, we all know that C stands for carbon, okay? And we are dealing with isotopes of carbon, okay? The number up top is going to be our mass number. Well, how do we know that? Well, our mass number is the sum of all the particles in our nucleus. So all the protons and all the neutrons. 6 plus 6 is 12. 6 plus 7 is 13. 6 plus 8 is 14. Great, okay? So that top number tells me the number of protons and the number of neutrons, okay? The number on the bottom, we should notice, is the same, okay? That number on the bottom here is a 6. Since it is a 6, we know that carbon atoms all have 6 protons, so that number at the bottom tells me my atomic number. Okay, or we can also say it's our number of protons. Okay, chemists use a special notation to symbolize an isotope. So we have something called a superscript, which is the top number. We like to say this is our mass number. The subscript is our atomic number that's on the bottom. Notice these are 2 isotopes of boron. One has a mass of 10, one has a mass of 11, okay? So this is isotope notation, and this is basically naming our isotopes, so boron-10, boron-11. If we hyphenate the name, that mass number is what we see at the end, okay? So again, one way to refer to isotopes is to use their mass numbers. So here you will see symbols for the 3 isotopes of carbon that we saw before. If we wanted to write these out, we would say that this is carbon hyphen whatever the mass number is, okay? So carbon hyphen the mass number. So this first one would be carbon hyphen 12, carbon hyphen 13, carbon hyphen 14, okay? You've probably heard of radioactive dating being done with different isotopes of carbon, okay? The average atomic mass of an element is the weighted average of the masses of the isotopes in the sample of that element, okay? So what you'll see there on the right-hand side, you see a sample of 100 atoms of neon. And so you'll see the blue spheres are neon 20, and those atoms have 10 neutrons. The yellow ones are neon 22. They have 12 neutrons, and then you have neon 21, which has 11 neutrons, okay? So we are going to always want to assume that we have a sample of 100 of these, okay? So take a look. How to calculate neon has 10 protons. That's the atomic number, okay? If we have 10 neutrons plus 10 protons, that gives us the mass of 20. 10 plus 11 gives us 21. 10 plus 12 is 22, okay? So let's assume that we have a sample of 100 atoms, okay? If we look at the sample picture that's up here, we would have 90 blue spheres. We have 9 of the yellow and 1 of the red, okay? So what we want to do, we want to say, okay, I have 90 atoms that have a mass of 20, so we take 90 times 20, and that gives us our overall mass of 1,800 AMUs, or 1,800 mass units for the neon 20, okay? I have 9 that have a mass of 22, okay? So what we're doing here, if you're not picking up on that, we're finding the overall mass of our sample and then finding the average, okay? And then we, do the same thing for the mass of 21, okay? And you add those up, okay? 1,800, 21, 198, that gives you 2,019 mass units, and you divide that by however many you have, okay? So we're looking at the average atomic mass of 20.19, okay? You should find that that is pretty close to what we have there on the periodic table. I believe on the periodic table it's listed as 20.17 or 20.18, okay? The percentage of each isotope of an element that occurs in nature is called the natural percent abundance of the isotope. We're not going to do really too much with this, but understand we can figure that out from what we just did with the neon, okay? And we can look at those percentages, because if we have, the neon 20, well, we have 90% is neon 20, 9% is neon 22, and 1% is neon 21. But, if we want to look at the formula to figure out that average atomic mass, we say total mass divided by the number of atoms. So when we figure out the total mass, we want to figure out what is the mass of that isotope and how many atoms of that isotope do we have, okay? Here's a sample question. We'll go over this when we do our lecture. Just understand we're going to look at an isotope of copper-63 and an isotope of copper-65, okay? The most common isotope of an element frequently has a mass that is closest to the average atomic mass given on the periodic table. To find the number of neutrons in the most common isotope, we want to round the average atomic mass to the nearest whole number and then subtract the number of protons that we have, okay? All right, so let's do a little check-in question. Nitrogen has 2 naturally occurring isotopes, okay? predict the number of neutrons in the 2 isotopes of nitrogen. Which isotope do you predict to be more abundant? Okay, so some things we want to do. Okay, nitrogen, I'm going to put A, which is going to represent my atomic number. Nitrogen has an atomic number of 7, okay? And the average atomic mass, okay? The average atomic mass from the periodic table is 14.01, okay? It says it has 2 naturally occurring isotopes. They're typically pretty close to that mass there. So we're going to say that we have a nitrogen 14, okay, and nitrogen 15. Stick my hyphens in there, okay? So nitrogen's average atomic mass is 14.01. We found on the periodic table. So we want to straddle that decimal number. So we're going to say we have a 14 and we have a 15, okay? Nitrogen 14, obviously 14 minus 7 gives me 7 neutrons. 15 minus 7 gives me 8 neutrons, okay? I would assume that nitrogen 14 would be the most abundant because its mass is closest to the average atomic mass that's given on the periodic table, okay? We will review this lecture and work on our activity in class.